Namaste. Welcome to this channel, Dr.ARM's Chemistry. We were discussing the topic Chemistry of Transition Elements, and we are now discussing the coordination numbers and geometry of transition elements or complexes formed from transition elements. We have seen the coordination number 1, 2 and 3 last time, and today we will discuss the coordination number 4. Coordination number 4 and 5. So out of this, if we take the coordination number 4, it is observed that this coordination number is very common. It is existing in variety of large number of complexes with different configurations, D configurations, starting from D0 to D10. So it is observed that these complexes are very common with the tetrahedral geometry. So we are expecting here two types of geometries. One is tetrahedral and another is square planar. Out of this, the tetrahedral geometry is very common. This is very common. Whereas this is somewhat less common. Less common. We are finding that the tetrahedral geometry, first of all we will discuss tetrahedral geometry. This tetrahedral geometry is found to be under the influence of steric effect, electronic effects and crystal packaging effects. So because of this, so we will see that this geometry is showing distortion due to one, steric effects, second, crystal packing effects, and third, electronic effects. So these are the reasons why the tetrahedral crystal structures of the transition complexes may undergo some degree of distortion. So the steric effects are largely observed when the ligands are bulkier in size, and in addition to this, the ligands are of different sizes and containing different effects, different elements present in the ligand, creating different effects. So these are a variety of reasons. In addition to this, the tetrahedral complexes, the tetrahedral complexes with D3 configuration complexes are very rare. They are not very common, they are less common. Now we will see the example of this tetrahedral complex here. So we will discuss the structure of the tetrahedral complex. For example, chromium is at the center, then nickel, we can show on this on other side also. Like this. So this is the structure of one chromium complex having the pentagonal chelate ring structures. Here you will find that the bond distance is 118 pm picometer. This is also 118. This is also 118, but this is 224 pm. So you will observe that these three bond distances are of one type, and this is longer than this. So this is because this axial chromium nitrogen bond is elongated compared to this bond. So this is also because of these electronic effects which are because of these Ma3 substituents present in the ligands attached to silicon Si. So the solid state structures are apparently simple anions. In some cases, the structures in solid state are apparently polymeric, and you will find that. So we will remove this structure. For example, CO F4 2 minus Ni F4 2 minus. So these are the two examples where we can have the polymeric structures. So these are polymeric structures. So it can have octahedral metal center. Octahedral metal center. Here fluorine is used as a bridging metal, bridging ligand. So here fluorine, you can see fluorine is used as a bridging ligand. Now we can have such tetrahedral geometries available with number of complexes in which the D configuration is ranging from D0 to D10. So we will see some of these examples here. So we'll see some of these examples. So first of all, if we see the D0 complexes, we'll find that VO4 3 minus, then CrO4 2 minus, then molybdenum MoS4 2 minus, then WS4 2 minus, MnO4 minus, then TCO4 minus, ruthenium Ru tetroxide, ruthenium Ru4, then osmium tetroxide OSO4, etc. So this is about D1 configuration. Then there is D1 configuration. So we have number of examples: MnO4 2 minus, then TC technetium tetroxide TCO4 2 minus, then Re radium ReO4 minus, ruthenium tetroxide ReO4 minus. So these are the examples with D1 configuration. Then D2 configuration: ApO4 2 minus, ReO4 2 minus, then D5 configuration: FeCl4 minus, then MnCl4 2 minus, then complexes with D6 configuration: FeCl4 2 minus, then FeI4 2 minus, then D7 configuration: COCl4 2 minus, there is only one. D8 configuration: NiCl4 2 minus, NiBr4 2 minus, then we have D9 examples with D9 configuration: CuCl4 2 minus distorted, then with detailed configuration ZnCl4 2 minus HBr4 Hg Br4 2 minus, then Cl4 2 minus, ZnOH4 2 minus, then CuCl4 3 minus, and NiCO4 nickel tetracarbonate. So these are some variety of examples which are occurring with tetrahedral geometries. Now we will see next type of geometry present with coordination number 4, that is square planar geometry, and this is somewhat less common compared to tetrahedral geometry. So we will see here is square planar geometry. So these are mainly associated with DH configuration, and here the electronic factors are strongly influencing the favor of square planar structures. For example, we can have, so here DH configuration is more favorable, or it is favoring the square planar structures. For example, you can have this PdCl4 2 minus, PtCl4 2 minus, then AuCl4 minus AuBr4 minus, then rudium RHCl, then PPH3 thrice, and trans, this iridium IrCl, then CO, then PPH3 twice. Then distorted structures. The example is IR PMA PH, this is P phosphorus, Me methyl, PH phenyl 2 4 plus, and another is rudium RH PMA 2 PME2 PH 4 plus. So these are two tetrahedral distorted structures. So each matrion has here D8 configuration, and this suggests state crowding. So you will find that the bulky groups PPH3, RBs, PME, PH2, etc. are bulky, and because of this the crowding steric effect is observed, and so this gives deviation from the square planar structure. So because of this bulky groups, so one group is smaller, other groups are in different size, so the square planar structure is distorted due to the crowding or steric effect. And rare example of D7 configuration is a rare example, and this is COCN4 2 minus COCN4 2 minus. This is a rare example of the square planar complex. So this is about coordination number 4. Now we will see the next coordination number 5, transition metal complexes, with next coordination number 5. So this class of coordination number 5 is having limited structures, limited examples or limited structures. So they have different types of arrangements under this title. So one is trigonal bipyramidal, trigonal bipyramidal, and second is square based bipyramid, square based pyramid, square based pyramid. So this coordination number is compared to tetrahedral, means coordination number for tetrahedral structure. This coordination number has also the limited options for arrangements, and these are seen here, that is trigonal, bipyramidal and square based pyramidal. So we will show here general structure of this trigonal bipyramidal arrangement. So for example, we can have this say Cl, we can have here say copper, so this is CuCl 4, or we can have CD or CuCl5. So it has 3 minus charge. So you can consider this arrangement. So if we see the shape, so this is a trigonal and this is pyramid. Like this. So we can have this type of arrangement. It is trigonal bipyramidal, and this is square based pyramidal, like this. So we can have one example of this, that is TC This is the example of square based pyramid. Square based pyramid. So we can show this square like structure. This is a square base and this pyramidal structure. Like this. This is a square base pyramidal structure. So we are given the two examples for this understanding. So here we will find that in this structure axial distance is 2.296 pm, whereas this distance 2.391 pm. 2.391 pm. So there is slight difference in the axial CU/CL distance. So comparatively, the axial distance is larger than this trigonal structure. So trigonal, these three CL which are lying in trigonal planars form are having same distance, but these axial around line which are lying around z axis are having this CL/CU distance relatively or comparatively somewhat larger. So this gives the distinction between the axial and this trigonal chlorides. We can have another examples of this type, that is CDCl5. Other examples, CDCl5 3 minus HgCl5 3 minus, and this CuCl5. So these are examples, CuCl5 3 minus. So all these are having detailed configuration. These are having detailed configuration. So the nucleon in these complexes has ground state configuration detail. In addition to this, you will find that many structures of this coordination number 5 are present, are having arrangement of ligands lying between this trigonal bipyramidal and this square based pyramid. These structures are changing, or these are not fixed in some many complexes. So these are the extremes arrangements. These are extreme arrangements. So all these are called extreme arrangements. And many structures are lying between these two extremities. This is because there is small energy difference. The energy difference, trigonal bipyramidal structure and this square based pyramid has small energy difference, and that is why the two structures are undergoing change depending upon the temperature available. So there are variety of arrangements lying in between these two extremities. So we can have other examples. So I will show here some more examples. Of these arrangements. So first of all we will see the square based pyramid. We have seen the this KB based structures, and now will this square based pyramid. So we have seen the structure. Now we will see some examples. With the D0 configuration, it has NB niobium, NbCl4, NbCl4, O, ox, minus. Then with the D1 configuration, we are having Mendelian complex V, acetate, AC, 2, also. Then another example, tungsten WCl4, O minus. Then TC Cl4, TCCl4, N, that is nitrogen, minus. Then TC Br4, N, that's all. Then D2 configuration has this example, TC Cl4, TCCl4, this also minus, and Re, radium Cl4, also. So these are few examples with these square based pyramids. Now we can have the variety of structures here. Ligands giving 5 coordinate structures are like this. Means there are many structures. We have already seen the structure, but in addition to this we can see here the structure of tungsten, that is W, and this Cl, then other Cl like this. So it has minus charge. Similarly, we can have NiCN5, NiCN5, 3 minus. So polydentate amines, phosphane or arsine, it gives with tripodal ligands. There are some polydentate ligands, tripodal ligands, in which the ligands are much bulkier . The ligands are much bulkier, and we can have the example like this. CO, Br, then here N, CH2, N, Ne, NMe2, thrice. This is plus sign. Then another example is RH, then SH, P, CH2, PPH2, thrice, and third example is Zn, N, CH2, NH2, thrice, Cl plus. So these are some examples in which we find that the polydentate amines are there, that is N. So these are amines which are of polydentate nature, means it has number of points of attachments. We can have other examples of these. We can have other examples of this coordination number 5, and this is XCF5, XEF5 minus. So the structure of this it has structure this is pentagonal planar structure. So many structures means there is small difference between the trigonal bipyramidal structure and this square planar structure, and therefore many structures are ranging between these two extremities, as we have seen earlier. So there are it is observed that many structures are switching over from TBP to square base pyramid and square base pyramid to TBP structure because of a small energy difference. We have another examples. We have many examples such as FeCO5 and PF5, phosphorus pentafluoride. So these structures are confirmed on the basis of their C13 NMR and F19 NMR. So they are confirmed with C13 NMR and here F19 NMR. Spectroscopic results, that is PICs, are used to identify the structures. So each of these is showing identical environment. So here C13 NMR has carbon, here in this case there is fluorine. So because of their similar structure, identical structure, their peaks are also of same nature. The spectrum is also of identical nature or identical environment in solution form. The TBP structure and square pyramidal structure have different peaks. Their interconversion time is fast, which gives only one peak. Now, if the two structures, that is TBP structure and this square base pyramid structures, there we have know that their energy difference between them is very small, and because of this they are constantly changing from TBP to square base to again TBP structure. And because of this, if we take the NMRs of these structures, we find that the intermediate structures are when the time is fast, then the spectrum gives only one peak. When the time of conversion is very fast conversion, then it gives only one peak of NMR. So this shows that the structure is undergoing interchange. If we found that, or when the time of conversion is large, then only we will get different peaks. Different peaks are observed in that case. So the time of interconversion is important. In solid state structures, we have seen various examples just before this. So is square based pyramid with doubly bonded oxygen at a apical position. So we have seen the various examples in which the oxygen is at the apex position and it is doubly bonded. For example, so we can have another example, that is CuNH3 2 plus. This is square pyramid in ammonia. So it is square pyramid. So as we have seen earlier, the structure of square pyramid is understood very easily. So this is about the coordination number 4 and coordination number 5. Okay, we will see the next example of helium. VO AC AC twice. AC twice. So this is a square pyramidal structure. This is also a square pyramidal structure. Now we will see the structure of this as this picture is obtained from V2O5 plus twice this CH3C double bond O CH 3 double bond O CH3. So it gives this product. Now here we have to verify whether this bond is single bond or double bond, and this can be done here. If we see the V double bond O shows higher absorption, at 980, about 980 per centimeter. Whereas the single VO shows single bond shows absorption, (480) per centimeter. 480 per centimeter. So this is the observed value of absorption band in IR spectrum. So this is this structure, that is V vanadium double bond oxygen, is confirmed with the help of this value. And for our reference, it is given that the single bond between vanadium and oxygen shows absorption at 480%. So this is our observation. So with this we can confirm that this bond must be double bond. Oxygen, this bond with oxygen vanadium bond must be double bond. So we will stop our discussion here and we will continue the next point in the next lecture. So till then, goodbye, see you next time. Please subscribe to this channel and press the like button and bell icon. So thank you very much for watching this video.